quantum communications in Spain. The workshop is divided in 6 sections. As you can see here, is sections of half an hour. We will make 2 breaks of 15 minutes. And we have very, very good speakers. And the first one, the main one is Davide Bacco. Davide is professor at the University of Florence, and he's co-founder of Quantum Telecommunications Italy. And he will give an overview of classical and quantum cryptography and quantum internet. And this will be the first 5 sections of the workshop. And then for the last section, this is about use cases of the QKD link that we installed between Santiago and Vigo with equipment from QTI. And the speakers will be Gonzalo Velázquez and Diego Cifrián from ITG, the Instituto Tecnológico de Galicia, and Gabriel Carral from Gradient, that is the Centro Tecnológico de Telecomunicaciones de Galicia. And with this, I give the word to Davide, that is our main speaker, and I'm going to give him the... Now, Davide, you can present.
Good morning, everybody, and first of all, thanks a lot for the invitation. Let me try to share the slides.
Mm-hmm. Should we put which kind of layout?
Does it work?
Yeah.
Yes.
We're seeing the presentation.
Perfect. That's good. Okay. So let's slowly get started. And again, thanks for the invitation. It's a pleasure to let's say, to dive into this long seminar. And if possible, I would like to keep it quite informal in a sense that the seminar is divided into sections, as it was anticipated by David. And so maybe we can try to ask questions at each session, or let's say before the break, after the break, let's see how it goes. So, and for the section, you can raise your hands, or you can also write in the chat, and then maybe somebody else will help me to go through the questions. Okay, let's get started. So the agenda for today, actually, it has already been introduced, but we'll try to give you, let's say, the full menu of a day. We will start from a very basic introduction to cryptography. So what does it mean, cryptography, why it is useful, and how does it work? Then we move to the challenges that we have today in classical cryptography. So actually we introduce the main methodology for sharing keys, and then we introduce the concept of asymmetric keys, symmetric keys, pre-shared, and this type of solution. We will move on to quantum cryptography, so the main topic of the seminar, and then we'll dive into, let's say, all the different type of protocols, comparison, and tables, practical implementation, challenges, and all these cases. Then we will move towards, let's say, the next phase. So we understood how it works, but we want to see basically how QKD can be used in today's infrastructure. How do you use it in our lives? So how can we benefit from this technology? Then the last part, let's say, will be a little bit more futuristic, in the sense that we will introduce the concept of quantum internet, and how does it work, why is it useful, why do we need it, and I will actually conclude with one of my research topic at university, which is actually basically my main research topic, which is multidimensional quantum states, and I will also give a slight touch on this direction. Okay, let's get started. So cryptography and key distribution methods. Cryptography, what does it mean, cryptography? So the word cryptography is a combined word. And actually, it is a composed word by two other words. The first one is cryptos, coming from Greece, and from the ancient Greek, that it means hidden secret. And the second one is graphene, to write. So in other words, cryptography, it means that it is the practice and the study of different techniques for secure communication between two or more parties. So we want to find a way to communicate with another party in a secure way. That's the meaning of the word cryptography. To help basically in our discussion, in our seminar, I want to introduce three characters basically in this seminar. The first one is Alice. That's usually sometimes called just A, or but I call her Alice or point A. The second one is Bob. So let's say usually the receiver. So Alice is the transmitter, Alice is the receiver. And the third one is Eve, the eavesdropper. But she wants to eavesdrop, the communication. She wants to eavesdrop our key. So she's the one that wants to break our communication. So this character actually will follow the entire presentation. So, but I think it's good to bring with us and to keep it clear. Let's do one step further. Okay, so cryptography. How does it work? What does it mean? As I told you, we start from the beginning. We have Alice and Bob, and they want to communicate. Alice wants to send a message to Bob, and the first message is actually this one. So, hey, Bob, do you want to know the name of the best city in the world? This is just an example. So these characters, basically, by using the ASCII or ASCII code, can be translated into a string of bits. So each basically character can be translated into a string of 8 bits. So if you look online, if you translate the word hey, you will see that the word hey is composed actually of a string of 8 bits, 8 bits, and 8 bits. If you goes on, you can basically translate each character into a string of 8 bits. So after we have made this translation, so we move from characters to bits, we need to use basically what is called the encryption protocol. The encryption protocol is just, say, a mathematical protocol. It could be just, a mathematical operation like a sum or a multiplication. And in order to do this encryption protocol, what you need to have is a key. And in this case, it is a yellow key. But the question now is, okay, but what is a key? A key actually is another string of bits. In this case, these bits should be random and should be secret. Later we will see it. Okay, let's assume that we have all the ingredients. So we have a message and we have the key. We apply this operation. It can just be, a sum between these bits. And what we get is called ciphertext. So this ciphertext actually is the text, and it is basically the message that you want to send through your communication channel. What type of communication channel can we use? We have different and many communication channels. We can send a message through internet. We can send a message through optical fibers. We can send a message through a free space link. We can use 5G, 6G, Wi-Fi, whatever you want. So space channel. So it's up to the customer to send the message where is needed. But the main peculiarities of these, let's say, ciphertext is that if somebody try to eavesdrop the message, what he or she will get is actually a noisy message. Because, the message is encrypted and it is not possible to read the original message. Only Bob, who is actually in charge, who actually has another key, so the identical key as Alice, it is actually able to decrypt, so to make another operation, which is the opposite of encryption, and to restore the original message. So basically, as we understood, the process is quite clear and linear. We start from a character or from an image. This is just an example. We translate it to bits. We encrypt the message with a key. We transmit it through a fiber channel, optical channel, or whatever you want. Bob receives a message, and then, he can decrypt the message by using basically a similar algorithm, and he can get the original message. So you see the point which is very important in this slide. We are basically moving the concept of sharing a message in a secure way to the question which is how do you actually share the yellow key between Alice and Bob? Because at the end of the day, what they need is just that they need a key to encrypt the original message in order to keep secure. So that's the question that I put here, and we get answers in few minutes. So how does it work today? So do we have these yellow keys? Yes and no. We'll see later. But basically, most of our communications is secure by using the so-called asymmetric encryption. Why is it called asymmetric? Because in the first slide, we have actually a yellow key both sides, and this is the case of symmetric keys because it is the same identical keys shared between two locations, between Alice and Bob. Counterwise, so in our daily life, most of our applications are based on the so-called asymmetric encryption. And we introduce the concept of public and private keys. We start always from where we have Alice and we have Bob. We have a message, here is very short, it's just, hey. We can still have an encryption, let's say, mechanism. But in this way, in this time, we don't have a yellow key, but we have a green key. This is, and Bob has actually a different key, which is a purple key. So the green key is also called, public key, and the purple key is called private keys. Of course, between these keys, there is a relation, and now I will explain this type of relation we have. So how does it work now? What is happening at the moment? So Alice says this message, she can encrypt, using the same concept that she used in the previous slide, but this time she will encrypt with a green keyword message. And she's going to get the ciphertext, she's going to translate it through the fiber, and then it will receive it Bob, and Bob can decrypt the message, okay? So you can say to me, okay, so it's very similar, very simple, and there is no problem, right? Here, what I didn't tell you yet is that there is a strong assumption. And the assumption is that this one. Let's stop for a second and let me focus on this kind of operation. If I give you two numbers, like for example, like 12 times 13, and I ask you, what's the result? You can type or you can think about it. You get 156. So it is a kind of an easy way to do. And you can do it, let's say, on your own or with your calculator or as you prefer. But on the other side, if I gave you the number 126 and I ask you, which numbers did I use in order to get 126? So did I use 12? Did I use 3 times 4 times 13? So you don't know which numbers I have actually used in order to give a result of 156. So basically, this is a very naive example, but it's just to explain you that the security which is behind the public and private key methodology is called computational assumptions. What does it mean? It means that we are basically assuming that there is nobody in the world which is actually able to decrypt our message in a time which is actually important for him, for her, and which is useful. So we know and say that, this type of operation is very, let's say, difficult to guess, in the sense that if you increase this number, you will get, a very complicated number, and then if you need to find the numbers that we used, is going to take a lot of time. But we don't care in the sense that the communication is actually already been established, and everything is okay. But we need to stress the point that this type of security is called computational security. So we know that there is a limit, but we know also that, I mean, we assume that nobody is actually able to compute this type of operation. So up to now, I mean, everything is good. So we should be happy, right? In the sense that we have been working so far for many years and everything seems okay. The main issue comes actually, and the answer is no, as you know, and it comes from one of the, let's say, biggest, technology, or let's say biggest device, which is gonna come in the next years, which is called a quantum computer. So let's start from a concrete example. Let's say that, I mean, we have, to solve a maze. So here is our maze that we have to solve. And we have an entrance and we have, let's say, an exit. And we have to find a way to get from the entrance to the exit. If, we are working with classical physics and we take a particle in classical physics, how does it work here? I mean, what can we do? Basically, the particle will try to get to go one way, to take one path, and I mean, we realize that it's wrong. Then we move to say to try another path, and then it's still wrong. Then we try again, and then at the end of it, so we try. I mean, we find the solution, right? In the sense that this is, also how our, let's say, brain will move inside basically a maze. So we try, each time, basically we try different paths in order to get to the solution. On the contrary, what is happening basically, if we move the same problem to, the quantum physics, so we have the same problem, the same maze, but the difference is that we don't have anymore basically a classical particle, but we have a quantum particle, like a photons, for example. The photons, behave differently from, let's say, the classical particle. And then, we exploit the principle of superposition. And what happens? Let's have a look again. All the paths are explored at the same time, and we get to the results in a very, very fast and efficient way. Okay, this is a very, again, naive presentation and examples, but it's just to give you, a concrete example that a quantum computer can solve specific problems in a very fast and efficient way. So, I don't need to explain, what is a quantum computer. I'm not talking, too much about quantum computers today, but this is, this is a picture from IBM that I took online. And this is one of the, say, different technologies which has been, say, exploited for making a quantum computer. A quantum computer is a quantum device, so it is based on the laws of physics, which is able, in principle, because, at the moment we don't have, today, a full functional quantum computer, but we have prototypes. But at some point, in the next years, we'll be able to solve some of the biggest problems that we have in a very fast and efficient way, which are not feasible for, classical computers, or let's say also high-performance computers that we have. Okay, but the questions could be, okay, but you are showing to me the quantum computer about how it is related to classical encryption that we saw a few slides ago. And the answer is actually reported here. I'm not showing, let's say, too much plots or complicated maths today, but this plot is quite important. So try to follow me on this graph. On the x-axis here, we have the dimension of the encryption key. So the keys that you showed before, the blue and the violet and the green keys, one of it, so it's reported here. Here is the time to break an encryption key on the y-axis. So how much time do we need to break an encryption key? Let's make a concrete example. So if we take a key which is 1000 bits, this here, and we take, I can say, a state-of-the-art actually computer, which is more or less here, it will take around 1 year to break these keys, basically to find the numbers that we have been using to multiply together in order to get to create these keys. But on the other side, if you take a quantum computer and you take a keys of 10,000 bits, it will take about 3 seconds to break your keys. So what's the take-home message here? The quantum computer, it is very, very good in, let's say, eavesdropping the ways that today cryptography is based. And for those of you that is not, let's say, doesn't know, basically one of the algorithms which is actually very vulnerable to quantum computer is RSA. And this type of cryptography, let's say, basically, you will not be sure when a quantum computer will be available. So what do we do next? So there are different ways of coping these problems. And now we're going to try to go step by step and to explain basically what you can do. So in this table, I have summarized the different ways that we have today for distributing keys. What does it mean? It means that here we're not talking about different type of encryption, decryption. Here we just say, okay, how can you distribute keys between 2 or multiple users? And then we try to compare them on this table. So the first one is actually elliptic curve Diffie-Hellman, which is, asymmetric keys, which is vulnerable to quantum computer. You will see later. The second one is post-quantum cryptography, which is a way, let's say, to distribute keys using classical communication schemes and classical cryptography. But here we don't use, let's say, the same math that we use in ACDC, but it's a different math. And at the moment, we believe that this type of cryptography, so the post-quantum cryptography, is actually robust against a quantum computer. What does it mean? It means that if you use a PQC algorithm, the scaling of how to break a key that I showed you in the previous slides is not as fast as in the other one. So it is secure against a quantum computer, in principle. I say in principle because since we don't have a quantum computer, we don't know how it's going to work later on. Then we have a pre-shared keys. Pre-shared keys is actually still very used today, and I'm going to give you a few examples in a minute. And then we have quantum key distribution. So quantum key distribution will exploit the laws of physics, and it is unconditional secure because we move the security from a computation assumption to the laws of physics. But let's go into the table. Okay. So security basis. So in the ACDC, we have elliptic curve discrete logarithm problem to solve. Then we have PQC, we have lattice codes, which are different codes, which are robust against basically quantum attacks. Pre-shared is secret key that we shared before basically our communication. And then QKD is quantum mechanics. Quantum security. As I said, elliptic curves are not secure. PQC is secured. Pre-shared is not secure if intercepted, in a sense that if somebody is actually intercepting the courier, basically it is intercepted. And QKD is probably secure. Key exchange method. How does it work? Here basically is a public key cryptography, so private and public key, as I showed you basically in the previous slide. Pre-shared keys, what does it mean? It means manually or electronically shared. So when you go to somebody's home, or when you go home, basically you need to install your new Wi-Fi. Basically what you're doing is actually pre-sharing a keys between your modem and your smartphone and your PC. And when you're going around and you take your camera, you put your QR code or a new Wi-Fi, is actually exchanging a pre-shared keys. So the Wi-Fi is actually pre-shared keys. If you move this context to, let's say, military applications, still, what they do is actually they pre-share, but they don't do electronically. They still do it with, let's say, a luggage, and they exchange basically luggage between the one man and another man. That's still how it works. QKD, we're gonna see so later, but basically we use principle of quantum mechanics. It could be free space optics or whatever. Efficiency. So ACDC is quite fast, so RSA or ACDC like Diffie-Hellman is quite fast, so small keys, low override is quite fast, and also pre-shared keys are usually quite fast to share. On the contrary, you need to keep in mind that the PQC, I mean, it is a good protocol, but it has a higher computational overhead. So it takes a lot of time to process basically these algorithms to exchange your keys. So it's not to say everything is positive. And also, I mean, QKD, I wrote here slow in a sense that you need to wait that your photos basically are traveling through a fiber and that to do all the operation. So it's not instantaneous, I mean, sharing the keys, but then we will see that it's not so important. Key size. Key size also here, it depends on implementation. So usually a CDC is 256. I mean, a PQC is about 1,000 bits. Pre-shared is usually 256 or 512. It depends on the type of protocols. And the QKD, we understood that it depends on implementation, right, of what you're looking for, but you can change the dimension of your keys, basically. Real-world usage. So examples of Diffie-Hellman, it could be TLS, SSH, VPNs are all using, I mean, this type of security. So it is widely used. PQC is an emerging adoption in the sense that it's coming. I mean, we have already, I mean, let's say newcomers. So we are actually, I mean, also new standards which are put online. And so it is for sure, I mean, the new trend. And regarding pre-shared keys, I mean, again, it's still very large used. I also mean Wi-Fi, IoT, I mean, UPA, this type of pre-shared keys, I mean, are quite used. And QKD, I mean, right now, I mean, I wrote here limited in a sense that it takes a little, let's say, it is, let's say, quite expensive compared to other methods. So, and requires special hardware. But then, I mean, we will see that it gives you, I mean, the best security ever. Vulnerability to the interception. So how can we intercept these? The first one, we cannot. Basically, we have many in the middle attack can be done. The second one is actually resistant to the many in the middle, depends on implementation, but there are some demonstration on these. Pre-share, if the key is leaked, if you intercept the courier, I mean, security is gone, and there is no other way to do it. So the only way to get basically, I mean, the 100% of the detectability of an eavesdropper is to use a QKD. So you say that you can spend a little bit more in terms of hardware, you need a special hardware, but then you can eavesdrop, basically your eavesdropper cannot get any information on your quantum keys. Deployment cost, the first one is low, and also, I mean, pre-shared is very low. And I wrote moderate on PQC and QKD because, I mean, PQC is not coming for free. I mean, you need to update, I mean, a lot of devices, and you need more computational power. So it's good to take it in mind. Scalability, I mean, ACDC, PQC, and pre-shared can work everywhere independently from your channel medium and channel communication medium. On the other side, QKD, I wrote fiber, but it could also be free space, satellite, whatever. You need an optical communication link between your transmitter and your receiver if you want to exchange basically symmetric keys with QKD. Long-term viability. What do we expect in the long term? So a CDC will be broken by quantum computers, not feasible, not scalable. PQC, I mean, it is secure again, future-proof. So again, a quantum threat, I mean, for now. And pre-shared is not ideal, but basically QKD, I mean, I wrote, I mean, future-proof, but work to be done in a sense that there is a kind of a little mismatch between, let's say, the theoretical implementation, the theoretical proposition and the implementation that we have in current QKD systems. But I mean, for sure, these are all things that can be solved, they can be resolved in the next years. So we expect that, I mean, basically the two ways of sharing keys in the coming years will be PQC and QKD. Okay.
Sorry, Davide,
please.
from the previous slide, because there could be a false friend
for between Spanish and English there. In quantum security, what do you mean by probably secure? Because it's not likely secure to be the QKD, but it's a demonstrated security because of the physics, right?
So you mean here, sorry.
Yeah, because in Spain we have a fault friend there that probably is like likely secure.
Probably secure, no. In English means secure.
There is a proof.
Okay.
Yeah. Yes. 100% secure.
Okay. Thank you.
Yeah. So it's actually the first. I mean, we should replace it with unconditional security.
Yeah.
That's what we should write. Yeah. Information theoretic security. Yes. If there are any other questions, we can take another first session. Otherwise, we move on with we move on with QKD.
I don't know if in the chat. No. At least in the chat there are no questions. I don't know if
someone wants to ask something directly or put it in the chat. But if not, you can continue, David.
Good. Okay. So now we move on the main topic of the seminar, so quantum key distribution, protocols, and state of the art. Okay, so we still have Alice and Bob always there, and then we have also Eve in the middle. And here the concept is different. Okay, so let's start what we want to do. We have to share keys by using quantum key distribution. What does it mean? It means that we don't use anymore the classical physics, but we use quantum physics. We use single photons, so let's say, or weak coherent pulses, so single particle of light for transmitting our photons. We will see how it works. And then we need to keep in mind that QKD, it is the only way, and it has this special property. We have the unique ability to detect an eavesdropping in real time in the quantum channel. What does it mean? So we have our scheme reported here. Alice and Bob, they want to distribute a secure key. They need two different channels, a quantum channel, which is reported in blue, and a classical channel. So the quantum channel, basically, it can be a free space, fiber, underwater, a space channel, whatever you have in mind. A classical channel, so the yellow one, can be whatever, can be internet, can be Wi-Fi, can be 5G, whatever you can use. So in the quantum channel, basically, Alice and Bob are sharing keys, photons, and these photons behaves like, quantum particles. In quantum particles, we don't have the same laws as, classical physics, so there are special laws. Indeed, what are the main, let's say, laws that we are exploiting in quantum cryptography in order to exchange the keys? We have two postulates. The first postulate is this one. So every measurement performed in a quantum system necessarily perturbs the systems. So we have Alice and Bob. They are sharing a photon in this way. It is a red photon. Nobody is in the middle, and then Bob is happy. On the other side, if Eve tries to tamper the communication, let's see it again. So here we have nobody in the middle, and Bob is happy, and we see the photon of Alice. On the other side, here this dropping, she's trying to measure the photon, she's trying to perturb the photon, and Bob will detect what is happening. So this is the first, basically, law that we are using in order to keep and to guarantee the security of QKD. Then we have another important law of quantum mechanics, which is the second one. It is not possible to make a perfect copy of an unknown quantum state. What does it mean? So here we saw an example, but basically Eve, she wants to modify, try to measure the photons. But let's say that she wants to copy the phantom state and then to resend it. It is not possible. It is guaranteed by the laws of quantum physics and basically the postulate of quantum mechanics. Basically, by using these two photons, we can guarantee the security of quantum key distribution. Let's do one step forward. But so, how do actually can they exchange keys between Alice and Bob? That's the first question. And let's focus on one property of light, which is polarization. I'm sure that many of you, is familiar with polarization, and which is 1 degree of freedom of light. And what basically we can do is that basically we have Alice, which is preparing a photon in horizontal polarization waves. So let's say that we have Alice that has this red photon, which is horizontally polarized. Bob, in order to measure the photon, he can choose, let's say, he can choose a filter. The filter can be, let's say, identical, so horizontal, or it can be a different filter. So if Alice prepares a single photon, which is horizontally encoded, and then she sends through the channel, and Bob measures with the same filter, there is a correct measurement. On the other side, if Bob changes the measurement, let's say that he wants to measure with a vertical filter or with a blue filter, what is happening is that if Alice prepares horizontal photon in red, Bob tried to measure, but actually, the measurement is not good because the photon is absorbed and the measurement is not conclusive. Again, this is a naive example, but just to give you an overview on how basically polarization can be used for making a kind of a encoded technique. Let's do one step further. Alice has a bit sequence. Let's say that this one 01001, and Alice chooses a different polarization, like for example horizontal, vertical, and horizontal. So 0 is horizontal and 1 is vertical. Bob on the other side can choose different filters, blue or red. So the first one, he chooses a red filter, and Alice has a red photon. Then she will send it through the channel, he will measure, and then he will register basically a horizontal photon. It means that it is 0. Alice she sent a blue photon this time because she's following the sequence. But Bob, since doesn't know, and then he's going to put another red filter to measure. In this case, basically the photon is actually absorbed, and we'll get not conclusive measurement. So we'll put an X on this sequence. By following this way and this sequence, what is going to happen is that basically at the end of a process, Alice and Bob will share basically a string of bits. But a string of bits, it is actually, basically a key. And it is the yellow key that I showed you at the beginning of the presentation. So at the end of the procedure, Alice and Bob have a secure cryptographic key. So this is a very high-level presentation of the QKD. And now we move on to, let's say, the more scientific part. But it was just to give you an example how basically photons can be used exploiting polarization to encode a 0 or a 1. Okay, how are we doing with time? That's okay, perfect. So QKD, so we understood that it is a protocol, so a quantum distribution protocol exploiting quantum mechanics, for distributing symmetric keys. But then, as in the different other fields, we have different type of QKD protocols, and we need to be able to navigate inside them. The first thing that we need to take into account is the different type of sources. So basically, there are two types of sources. One is called the prepare and measure, and another one is called entanglement-based. Prepare and measure is basically like the word is saying, you have your transmitter, you have your Alice, which is preparing a quantum state, sending through the fiber, and Bob is measuring your quantum state. 95 or 90% of, say, commercial systems are based on prepare and measure. Entangle-based, here we are exploiting another special property of quantum physics, which is entanglement. So this special correlation between particles. Here we don't have, let's say, two parties, but usually we have three parties. You have an entangled source in the middle, sending photons from to Alice and to Bob, and they are measuring basically these photons. So here we can basically differentiate based on the source if we are working with a prepare and measure or if you are working with an entangle-based source. Then we move to the modulation. Here we have three different types of modulation. We have discrete variable, continuous variable, and distributed phase reference. Discrete variable, it means we are using discrete degrees of freedom of light. For example, polarization, time beam, phase, frequency, path, space, well, then we will see later. Continuous variable is a different way, and then here basically we are going to use amplitude and phase of optical light, basically. The third one is distributed phase reference. It is kind of an old type of protocols, but I always like to put inside because it is still somehow used. And here, basically, what you use is a different phase between sub-pulses of your light in order to encode your quantum states. I'm going to explain later on a little bit more details. In order to complete the classification of the QKD protocols, we need to focus on the different implementations that we might have. The first one is one way. We have Alice on one side, Bob on the other side, and then the light basically is traveling from Alice to Bob. The second one is a two-way implementation. It was used in the past, not anymore, but it was used. Then we have Alice preparing a state of light, not quantum, sending to Bob. Bob is actually modulating at the quantum lander and sending it back. It was used for coping the problems of polarization into fiber, and then in order to basically to counteract and to solve this issue, it was used to this two-way protocol. The third one is MDI, somebody might know. And it is MDI stands for Measurement Device Independent Protocols. And in this type of protocols, you can also include the twin feed protocol. And here you have a third party, actually, where you have Alice and Bob, and usually, Charlie. And here is the change of paradigm in the sense that Alice and Bob actually are sending photons towards a third party, which is untrusted in the middle. And which is the reason why it's called measurement device independent, because the measurement are actually device independent, so we don't care about who is measuring our photons. It could also be an eavesdropper. So it is quite, a good protocol for future implementation and for difficult situation where you don't trust, let's say, your producer. Okay, let's move to, let's say, one step forward. Let's compare the different modulation format. As I told you, we have basically three different types of modulation format. We have a DPR, the discrete variable, and the continuous variable. The DPR and discrete variable are actually using single photon detectors as a detection technique. So it means that here we are using single photons, and you do need single photon detectors. Continuous variable systems don't use single photons, they use coherent states, and you use coherent homodyne or heterodyne detection, which is the main difference also between these two protocols. If you move to the post-processing that I didn't introduce yet, but I will do it in a few slides, it is basically what you need to do after you exchange your photons. In DPR and DV, it is quite simple and straightforward, well known and easy to do it very fast. On the other side, continuous variable, this is quite complex error correction code, and it takes a little bit of time. If you compare distance and rate, you see that there is actually quite a different situation between DPR, DV, and continuous variable. So DPR, actually, they can reach more or less 100 kilometers, but then there are some drawbacks on the security level. The discrete variable are the most known and or secure protocols which have been investigated so far, and there are demonstrations of more than 500 kilometers of point-to-point link. If you include the twin field, also it can go up to 1,000 kilometers. So it can reach, quite a long distance application. On the other side, continuous variable, they reach 100 kilometers, but it was a special condition. But usually, if you take, if you compare commercial product, it is well known that the continuous variable, it is more suitable for short distance metropolitan communications. On the other side, what you have is that the rate is actually quite different in a sense that DPR and discrete variable, if you don't include multiplexing special detectors, but you just stay with commercial systems, you can reach a few megabits, yes, but I mean, on the other side, continuous variable can reach actually in principle 100 megabits of secure key generation. Let's move to the last one, which is the security, and let's have a small discussion about security. So regarding the DPR protocol, as I mentioned to you before, it is quite an old type of protocols. And in this category, you might know the protocol called COW, Coherent One Way, which has been used by DiCantic for many years. And it was a very nice implementation. And but actually, so it has some drawbacks in terms of with different type of quantum attacks which can be done in the systems. So from this type of protocol, actually, the main issue was that there was the coherence between the all quantum state propagated through the channel, and it was not possible basically to extend to have the same level of security as in the discrete variable. So in the discrete variable, if you include decoy states and other basically solution for counteracting a different type of attacks, you can get a general, you can basically be secure against general attacks. You can include finite size, and you can also include, I mean, all the side channels can be basically removed from your systems, which are quite low. In terms of continuous variable, also here, I mean, there have been a lot of progress in the last 10 years, actually 5 years, and there are solutions against basically general attacks, including Gaussian modulation. And but since, let's say, it is a more relatively new protocols, I mean, I would say that a little bit of more theory is needed in order to get a better understanding on the main difference between the implementation and the theory which has been developed. Okay, let's move now. Let me see. Yeah, we can do it before we break. Okay. Let's move now to the discrete variable QKD protocols. The most well-known and used protocol is the BB84 protocol, which is, I mean, stands for Bennett Brassard. It was invented in 1984. What do we have? We have, again, always Alice and Bob, which are actually sharing, I mean, photons, which has different polarization in this case. And then at the end of the protocol, they exchange a secure key, the yellow key that I've been talking since the first slide. It is appearing here with different bits, K1 to Kn. That's what basically they have to do. How do we do it? Sorry, we use a little bit of, when it's not super clear. Okay, anyway. So QKD is divided in different types. It is divided in a quantum communication phase and a classical post-processing phase. In the quantum communication phase, in the case of prepare and measure, what is happening? Alice prepares a quantum state, she's going to send it through the channel, and Bob is actually measuring. After this, what would happen is that we have the classical post-processing, and then we exchange the secure keys. Let's go one step, I mean, further. So what is happening actually inside basically the systems? We have a quantum communication. The first thing is that after the transmission of the photons, we have the so-called sifting, which is a basic reconciliations. And it is done because basically in the first slide I actually omitted something because the different polarization that Alice is sending is actually 4 different states that we're going to see in the next slide. So they need to agree basically in which basis they measure, which is basically what is happening here. After this process, Alice and Bob will share the so-called row key. And the row key is the starting point for doing 2 different types of protocols. The first one is to do error correction. So to apply a protocol for correcting the errors which has been basically done during the transmission of the quantum states. To correct errors, you might want to use two protocols basically are most used. The first one is a cascade protocol, and the second one is LDPC protocols. These are the two main categories of protocols used in QKD. And the third process that you want to do is privacy amplification. So you want to remove basically privacy amplification or the leakage that you might have done in all this way of this round of communication inside your channel. At the end of the process, what you will get basically is the secure key, so the yellow keys between Alice and Bob. But let's see basically how it works in reality. So we go back to polarization. So as I told you, Alice has a string of bits, and she's actually encoding her bits in different polarization states. Here we introduce the so-called mutually unbiased basis. What does it mean? So Alice, she has to prepare, and Bob has to measure, in these two bases, basis plus and basis X. Inside the basis plus, you have vertical polarized photons, which we can be encoded in the bit 1, or horizontal polarized photon, which can be encoded in the bit 0. Similarly, in the base X, you have anti-diagonal and diagonal polarization states, which is referring to bit 1 and to bit 0. Why do we need basically two bases? We need two bases, basically, in order to detect any type of eavesdropping happening in the communication systems. Because if you have only one basis, what is happening is that the quantum state that actually you are sending is not quantum anymore, because you can be actually, you go back to a classical situation. And Eve can intercept and just basically send your quantum states over to Bob. Let's see, how the measurement is actually working. So Alice is sending all these quantum states reported here on the top. And Bob, he has to measure. Bob, for measuring, can use a polarization bit splitter, which is actually an optical component, which is able to divide, for example, if you put it in a horizontal and vertical way, is able to divide vertical and horizontal polarization. Alice is sending a vertical polarized photons, is going towards Bob, and Bob is measuring with a plus basis. So by using a plus, basically 100% of the time we will get a click on this way, and 0% of the time you get a click on this way, if everything is, say, ideal. On the contrary, if Alice is sending a plus 45, what is going to happen is that if Bob rotates this polarization bit splitter, so he can rotate the alignment in order to measure plus 45 and minus 45, and Bob will get 100% of the time the measurement in this way as well. I don't do the case of the opposite way, that basically if you put horizontal, 100% of the time it will go here. If you put anti-diagonal, 100% of the time we go here. What happens if basically Bob is measuring in the wrong basis? Here is the example. Plus 45 is going into basically the beam splitter, sorry, the polarization beam splitter. And if Bob measures with plus basis, so horizontal and vertical, it has an equal probability of getting click here or here. And on the same, that if a vertical photon is measuring the X basis, it has an equal probability of measuring here or here. So there is a 50% of chance, basically, of measuring one of the two states. And basically, it is a wrong measurement basis, and it is actually discarded in the shifting protocol. This is an example using polarization, but polarization is not the best degrees of freedom for working in fiber optics. Indeed, what we do, and actually, a lot of other groups in the world are doing, is to use time-bin encoding. What does it mean? It means that our quantum state can be encoded, again, in a Z basis or X basis. These are still mutually biased basis. And the photons can be encoded either here, so at time t0 or at time t1. So time early or time late. There is a small typo here, sorry for this in the presentation. So this is the Z basis. The X basis is actually the superposition between these two time beings, which is time t0 and time t1, with a relative phase of 0, with a relative phase of pi. Why do we like time bin encoding? Because it is suitable for single mode fibers and for long distance. It is extendable to, high dimensional quantum state. I'm going to show you later what does it mean. And it works very well with optical interferometers and modulators. So we can use off-the-shelf equipment to build basically QKD devices. How does it work with measurement in a time being encoding? Okay. So we have our quantum state. It is the same. I just design and draw a more weak coherent pulse here, more pulse compared to a single photons. And we want to measure, let's say, in the Z basis. The Z basis, what you have is basically if you measure, the time of arrival with a single photon detector, you can clearly basically refine and measure which of the quantum state has basically have been sent by Edison. The second measurement is in the X basis. So you need to measure, in order to measure this quantum state, you need an interferometer. And actually you need a delay line interferometer, which is a difference of tau, T1 minus T0. And you need to be able to resolve the phase between the weak coherent pulses. If the phase was 0, we'll get basically straight. If the phase was pi, it was reflected. The same principle of multi-random bias will apply here, because if you send this quantum state, the X state, inside the Z basis, since you have two weak coherent, you have equal probability of getting a click at T0 or at T1. Similar to what you have here in polarization, so 50%. Also here you have 50%. If you send this state, the Z basis, inside the interferometer, it will split basically in two paths, and then it will create a superposition, and basically you have a 50% of probability of getting a click here or here or here. So this is a way, basically, that you can encode, measure and propagate your quantum state encoding a time being over fiber. I'll do one slide more, and then we can have a break and actually, of course, questions. The slide is this one. So you showed me that it is possible, everything seems fine, and then you can use off-the-shelf equipment, but what are the problems? And we do have, a lot of problems to solve, otherwise we would not do research in this direction. So open challenges. The first one is distance limitation. We know that we use an optical fiber. We have a photon loss lose through the fiber. Then we need to put the concept of trusted node. I'm going to explain you later how it works. But let's say that we have a limit, the maximum distance for security exchange. It is quite clear that we can reach basically, a certain amount of distance with a single photons in a fiber. The same thing happens in the atmospheric interference, in the sense that in a free space link, still you have attenuation, you have other problems like turbulence, you have fog, you have rain. So you are limited in the overall propagation. The second problem that we are facing, it is the practical implementations versus theoretical ideas. What does it mean? To be very brief here, the point is this one. One thing is to write a mathematical description of physical laws on a piece of paper. Another thing is to go to the lab and to implement what has been written in the paper. So there are, let's say, some differences which has to be taken into account where you are, say, working and demonstrating your security protocol, which has to be, basically, it is quite an important field to be considered and to be exploited in the coming years. Then there is all the world of the quantum attacks, which is not entering too much into detail today, but you need to take into account that there are a lot of attacks, there are a list of attacks which can be done on a QKD system, and you need to, let's say, to find your way to find the countermeasures for your type of attacks. And there is a very nice document that we have also been contributing from the BSI, basically from Germany, in which there is a list of, I don't remember, but it was something like 100 attacks, both for discrete variable and continuous variable. And if you are interested, you can, I suggest you to read the type of, this type of document. Other challenges, scalability and integration, in the sense that at the moment, let's say that there are few networks, but big networks, should come in the coming years. And in order to enlarge the quantum networks, you need more devices that they're going to show you later. So we need to take into account that to find solution for networking and scalability and this type of networking. The last one is the key rate and throughput. I put it here, but because most of people sometimes said that, oh, the key rate generated by QKD system is not enough. But at the end of the day, we never face a problem in terms of commercial application that it was not enough, because the rekey time, so the time we change basically, the time which is passing by the rekey, so it's actually very, very long. But in general, I think that it's good to try to increase the key rate and throughput of a QKD system, which is one type, let's say, of limitation that we are facing today. Okay, so if you agree, I would like, I think we can stop for the 15 minutes now. But of course, if there are questions for this section, I mean, I'm happy to take it now.
Yes. Do you have any questions in the chat?
No.
No. I have just a small question. I read, I mean, I know that there is a paper, no, that about the COW protocol. It's a theoretical paper that they found a way to attack it. So that means that all devices, I mean, do you know if there is any experimental implementation of that paper, or is it still a theoretical thread, let's say?
So I know the paper quite well. I know also the authors of the paper, and it goes back here basically. What does it mean? It means that this is the reason why, I mean, I wrote that I said before that this type of protocol is limited, and the reason is basically that one, in a sense that it has been demonstrated that it is not secure, I mean, as it was thought to be. So it means that, let's say that they thought that it can reach 150 kilometers in terms of security. Based on the new papers, these kilometers are basically half of it. That's the limitation that you are facing. Okay. It doesn't mean that you cannot use, sorry, my headphones were disconnected. It doesn't mean that you cannot use the device anymore, but it means that it is a different type of limitation, right?
Okay. Okay, perfect.
And let me just say another thing. We need to think that there we were discussing about, here we're discussing about general attacks, so the most powerful attacks that Eve could do in a QKD system. But even, let's say, a collective attacks is something super complicated that requires, I mean, a quantum memory, and which is something, I mean, very, very difficult. Right? Yeah. We need to keep in mind also this point.
Okay, okay. Theoretical theory. Okay, so maybe we can stop for 15 minutes and resume at 11:20.
Perfect.
It's okay?
Yeah, you can continue, Davide.
Okay, good. So we understood how it works, so how QKD works, how we can exchange keys, and the importance of exchanging keys with different methods. We now, let's say, step a little bit back, and when we have a look from the top, and we try to see what is the state of the art on QKD. Of course, it's not exhaustive. I mean, I take a few examples just to give an overview. Let me start with the terrestrial link, so the state of the art on terrestrial link. The first one is the impressive network in China. The network is actually going from Beijing to Shanghai at the moment, but the new network will be ready in the next year. And this one was a paper from 2021, and it was already more than 2,000 kilometers. I don't remember how many nodes they have, more than hundreds. And so it is quite an impressive demonstration. According to the paper, there are, I mean, commercial users and clients which are actually connected to the network and using the quantum keys. The second network that I would like to highlight, it's the network in London, which has been realized by basically British Telecom. and Toshiba. And it is basically a 3-node network, and it was highlighted as a commercial network. And I know there was some agreement with banks then to use this network in the city of London. Another one that I really like to highlight is the one in Madrid, and I think you know quite well, I mean, what I'm talking about. And it is a super complex network made of different devices, different level of integration, and the work that, I mean, the group, I mean, of the center is doing is amazing in the sense of trying to integrate different technologies, different levels of key manager that we'll see later. So it is, I mean, quite impressive network, I would say. And the last one that I want to highlight is actually from in Germany, where there was this network realized by Deutsche Telekom. And it is connecting the city of Bonn with the city of Berlin. And if you look at the map, it is mostly basically a linear network, but it is good, and actually it is very, very interesting in terms of deployment. I'm not entering too much into details, but just to show that basically, I mean, QKD networks are expanding, and Europe is playing an important role in this, and more networks we will see basically in the coming years. Okay, let's move from terrestrial, so from Earth to space. And space, still we need to start from China again, because I mean the first entangled source from space was installed in the Michu satellite back in 17, 18, if I'm not wrong. And it was, I mean, a fantastic demonstration. So discrete variable system from space, sending entangled photons. It has also another source of BB84 protocol. Very impressive demonstration. What about CV? CV was this paper, and was a theoretical paper, pay attention here, but they demonstrated the possibility of doing basically continuous variable quantum key distribution from space to the Earth using this type of solution. But it is more tricky because, as I told you, I mean, long distance is way better to use discrete variable. Last but not least, I mean, again, China did it again. So microsatellite-based QKD was launched, I think, this year or last year, and then it was published this year. So in this satellite, they still use basically QKD protocol. I mean, you can see some more details here that they are working. They have 850 nanometers for the quantum communication and 1538 for classical communication. So it is another impressive demonstration. And I don't have the slides, but if I'm not wrong, I mean, basically there was a launch of satellite from Singapore recently, and we are expecting a few launches of quantum satellite next year. That's what I want to share with you. I mean, we're expecting from Canada, we're expecting also from Europe, again from Singapore, so a lot of exciting news will come. Underwater quantum communication. Why do I want to share with you this? Because actually it is another channel opportunity. And without entering too much into detail, what I want to share is this one. So underwater communication, when I said underwater, I'm not talking about a fiber which is deployed underwater, which is a different concept. I'm talking about free space underwater communication. So photons traveling inside the water. And it is super complicated, super difficult, and short range because basically water is absorbing all the optical radiation. So the overall distance that we can aim, I did a theoretical paper back 5 years ago, is actually less than 120. So it's 100 meters is what we can hope to achieve in, I mean, ultra clear water scenario. But there are some interesting demonstrations, some interesting projects. And I do have a slides later about the project that we are working on. And so just to share that there are a few groups in the world which has been exploring these, both mainly using discrete variable approach. and using also arbitrary momentum with different type of degrees of freedom. But so there are demonstrations, and it is quite interesting to work on this topic. Okay, so after this very generic and top overview of the state of the art, so where we are, let's move to the use of QKD keys. So we understood how to create a key. We know how basically, where we are in terms of worldwide, but how can we use a key? So what can we do with quantum keys? And in order to use a keys, the first thing that actually we need to do is to introduce the concept of key manager. Here I'm reporting an appliance from QTI, which is called QKME, so it's Quantum Key Manager Entity. And the first question is, what is a key manager? So it is an appliance which integrates basically key storage, so it serves for key storage and for key deployment. So basically it is a place, it is an hardware where we can store your quantum keys generated, and also for distributing these keys across the network, and to act as an interface between the quantum world and the classical world. So it is another very important appliance which is needed for implementing quantum networks. Other two things on this key manager. It is important. Why? Because it ensures compatibility and interoperability between different systems. And it also allows to have multi-vendor key manager entities or key manager interfaces, and networks of different vendors can be merged, can be, let's say, announced also by using the different key managers. Let's see how it works. Here I change the icon, so we move to let's say more professional one. So we have Alice and Bob, and we have a QKD system on the bottom. So we have a QKD systems with a quantum channel, a classical channel, let's say two fibers, and we understood that they can generate keys, and then this is the key that they can generate. These keys, after generation, it is saved in a database, let's say, inside the key manager, basically the hardware that reported here. The key manager needs also a channel, so it is important to keep in mind that the key manager needs basically, an inter-channel, an optical fiber channel, whatever you want to use, but they need to communicate to each other. For what? For implementing different type of protocols. For example, ETSI 014, ETSI 004, Cisco Skip, Nokia SMS, or Base Jump. So inside the key manager, basically, you have to run your own application in order to store your keys, but also in order to be able to give the keys to what? To the encryptors. Because in order to encrypt basically your channel, you need to get fresh keys to encrypt it, to secure your data. Let me try to explain the concept here, but I think it's quite simple. So on the bottom we have the QKD channel which generates the keys. The keys are stored in the key manager. The key manager can act as an interface between the quantum world, which is on the bottom, and the classical world, which is on the top. And how do they work? They work implementing API REST calls, so server and the client basically protocols, and what you do is to implement different type of protocols as reported here. I'm not entering too much in detail, but most of encryptors today they're using ETSI 14. Basically, this is the protocol that is quite preferred by the community and also of telecommunication devices. When I said encrypted channel here, so here don't take as a must that it should be an encryptor. It could be also a router, it could be a switch. So everything which actually is able to encrypt the traffic, but it doesn't mean that it has to be for sure an encryptor on this side. Okay, let's go one step further. So as I told you here, key manager is actually including, it is saving the keys from the QKD. But a key manager in general can save keys generated by different methods. And as I told you, I mean, there are four different ways of generating keys. So there is QKD, there is a PQC, there is a pre-shared, and there is Diffie-Hellman. So the first four methods that I showed in the beginning of the big table. But what about if let's say we have a key manager which is actually able to generate a different type of keys, and is actually able to XOR and basically to mix these keys in order to generate the so-called session key. The session key then, by using standard protocol like ETSI-14, CESGA-VQCC, blah, 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 can be passed to the encryptor. Why I'm putting these slides here? Because there are some, let's say, ideas, there are some implementation, and the key manager of QTI can also do that, I mean, with, let's say, an additional, an add-on basic application. It is possible to merge different keys, because, I mean, let's say that you are very paranoid and then you want to mix, you want to have a PQC and a QKD. Okay, the key manager can mix these two keys. But then let's say that in your side, the key manager, you do have also some pre-shared keys. And then you can mix all the three together. And so this is basically a way to increase the security by mixing the keys all together. And this is, I mean, a solutions that we have been suggesting and also using for some specific use cases. Let's move on. So beyond the point-to-point, I already mentioned these before, but we have some limitation when we talk about QKD. So we saw that research, I mean, a few groups demonstrated with 1,000 kilometers link, and also, I mean, other work demonstrated 500 kilometers. But at the end of the day, you do need the so-called trusted node. What does it mean? It means that in this case, we have your application, so your encryptor A, which needs to communicate with your encryptor B, which are located far away. How do you do? How is it possible that the encryptor A communicate with encryptor B by exchanging keys and have everything? What you do basically is you subdivide your overall link in sub-links. So you have your Edison Bob 1, Edison Bob 2, and Edison Bob 3, in which, and actually they will generate a key 1, so a key 2, and a key 3. How do you basically do? You have three different keys. You take the first key, you XOR the first key with the second key and the third key, and the first key is actually propagated through the overall channel. In this way, you have that your application A can communicate with application B, and both of them, they have the key 1, and the key 1 can be used for the encryption of real time of traffic. What's the problem? The problem is that you have the so-called trusted node. The trusted node, it is called trusted because actually the key 1 is passing here in clear. So basically it is, I mean, it's a point, it could be a point of failure, right? And so at the moment, we're using these technologies. There are different ways of securing trusted nodes. Of course, the first one is to be a physical security. The sense that it has to be in a special place, it has to be closed in a rack, and this type of solution. There are also combination of physical security and some mathematical approach that has been demonstrated. There are a few papers about it, and actually a new paper will come out from us next year. And but the long-term solution is to use the so-called untrusted node. I don't have time today to go into the details, but I mean there are few groups in the world which actually demonstrated that it is possible to basically create a quantum repeater, which is a repeater of quantum state, not breaking basically the laws of physics, and it allows the propagation of the quantum state from point A to point B without having the trusted node. Okay, before moving to the implementation, I want to share also the concept of software-defined network. What does it mean? So if you are familiar with classical optical communication, Software-defined network is a concept, which has been used in the last 15 years for managing, controlling, and basically combining all the different devices in a What security has been suggesting is to have a quantum software-defined network solution, and it means that a QKD system, including the key manager, can be controlled, can be monitored, and can be interoperable in a complex network. This is basically the concept of quantum, so the software-defined network in a simple style. There are already some standards which are not, let's say, very well defined yet, but there are also some implementations. And in QTI, we do have our implementation of our standards in our way, and actually we already sold them in a couple of QSDN appliances, inside the big network. And I will show you some example later. Okay, so actually this is not another session, but it's just to put on top of it and to conclude the session on real use QKDs before moving to the application of QKD. So quantum safe network, so today and tomorrow. How do we do it? Again, we go back to the telecommunication network, and the question is this one. If we have a network today, and the network is not secured against a quantum threat, how do we secure the network? Is it possible to secure the network today? Is it possible I have to wait tomorrow? I have to change everything? What can I do? And I try to answer to this question. So in a very naive way, I've divided the different layers of a telecommunication network. I have divided in two layers, the network layer and the encryption layer. The network layer, I put all the different devices on the same level. So we have switches, router, clients or computers and whatever. We are connected in a naive way, but just to give you an example. Then we have another layer, which is the encryption layer. The encryption layer is just for simplicity that I put in a different layer, but it can be included inside the same device. So it is not just a logical separation. It is not, let's say, a physical separation. It could be also just inside the switch, inside the router, that you have just an encryptor software or an encryptor apparatus inside your machine. The encryptors communicate to each other, maybe using pre-shared keys, maybe using private and public keys. So they communicate the way that they do today. But we also know that this way is not going to be secure in the next, let's say, years. So what can you do? What you can do is to add another layer. So without changing basically your upper layers, and you can do your layer of key distribution, management, and QKD. Actually, to be, let's say, more precise, you can put in a hybrid solution, so a quantum safe solution, where you mix your QKD with some PQC, and I try to explain the reason for it. So here in black, you have the key managers, different key managers, which can give the keys to the encryptors using ETSI-14 interface. So EF stands for interface. And the different key managers are connected with the QKD links in this case, this case, and this case. But here we don't have a possibility of running a QKD link. Why? Because maybe the customer doesn't have a fiber. Maybe the customer is moving vehicles. Maybe the customer, it has, let's say, is very far away and we cannot reach it, right? So there are many solutions, so many problems that where we cannot use QKD. So the idea is to have a mix of keys using basically PQC and QKDs to ensure your network. But why this is possible? Because the key manager will allow you basically to share and to distribute the keys across the network, to share these keys and to pass the keys to the upper layer, which is the encryption layer. But the keys which has been generated are secure against a quantum threat. So in this way, we secured the network, which was not secure basically a minute ago. This is a solution, let's say, for the next years in order how to implement quantum security. With this, I have concluded this session and I move towards the application. But let me ask if there are any questions on this session.
Diego, any question?
No.
No. I have a small question though, just for the audience. And in the key MAs, how do you secure the keys in the devices? I mean, because it's, you have a pool of keys, but in a hard drive, I mean, there is any securization inside. I mean, it's just.
Yeah. The question is quite clear. So there are different ways of securing keys inside the key manager. And the first one, or say the best would be to have another security modus where you store your keys, and then it could be used, let's say, in some specific ways. This could be a way. Other ways are to have basically, of course, in order to get keys, you need certificates. And these certificates have to be created basically by the key manager in order to get keys out and inside of it. And then there are some physical, implementation, some physical, let's say, constraints that we might put on the key manager. So basically, you need to act as, let's say, a critical device, and you need to close all the different ports. You need to basically to have firewalls, this type of things that has to be implemented. But I would say that so there are different levels of key managers and different levels of security, depending, of course, on the application.
Okay.
There's one question. Jaime is asking, how do you copy the quantum state?
So I think it is referring probably to the untrusted node here, right? Because so as I said, it is not possible to copy a quantum state, but what a quantum repeater is actually doing, it is actually creating an entangled photos between 0.1 and 0.4. And then since you are creating an entangled state, what you do basically is that it means that 0.1 and 0.4 are correlated. And since they are correlated, you can exchange the keys based on this correlation. So it will be different, a completely different way of doing QKD. So it will still not based basically on prepare and measure, but you need entangled base in order to propagate these systems. I hope I answered to the question.
Yeah.
Thank you.
Yes, understood.
Perfect. Okay. So let's move on. Application of QKD. So where do we actually apply QKD, and how can you apply QKD in general? The first implementation that we had, I know that many of you probably already saw this slide 20 times, but it was very important for QTI because it was the first milestone. In a sense that we created the first inter-countries communication with two different countries, in a sense that we create a small link between Italy, Slovenia, and Croatia during the G20 event, which was held in 2021 in the city of Trieste. The goal was to show basically to the European Commission and to show to the European countries that quantum communication was ready to be adopted, was ready to kick off, and to start making the networks. We always like, to say that this was, let's say, the first result of the EuroQCI program, because actually it was released just before the course of the EuroQCIs. And we were very proud of this demonstration. Let me go a little bit more in detail. So we create a link between Rijeka and Trieste. The channel was 25 dB, optical channel, we had 2 fibers. Then we had, actually here we had an optical switch, it was a kind of emulation optical switch. And then we have a link between Trieste and Ljubljana. But the channel were, say, too noisy and too long for the systems that we used at that time. And so we had to put a trusted node in Postunia. That was the concept that I introduced before. We exchange the keys inside, I mean, let's say the 3 cities, basically, and these keys were used to create a VPN, so a virtual private network, which was used for sharing a concert which was played between Ljubljana, Rijeka, and it was listened in Trieste by the ministries which were present in the exhibition. So this was basically just a demonstration, and it was basically for the purpose of showing a new technology. But it was impressive in terms of, let's say, what the technology could do at the moment. Based on this, which actually, and it was published in a scientific paper. Based on this, we started to produce our protocol, our systems, which is a QKD system based on BB84, using time being encoding with decoy state. And the standard systems today can go up to 30 dB of channel losses. And it can operate in single or in duplex fiber, but I'm not entering too much into detail about it. So this was the first implementation that we had in 2021 regarding QKD with a real concrete use cases. Highlighted some of the, let's say, most important use cases that we did in the last 5 years. And I'm not showing all of them to you, but it's important to show some of them. So quantum security for high capacity between data centers. So we had an implementation between 2 data centers in Greece, in particular in the city of Athens. So actually in QTI is included in the Telecom Italia family, so team group. And within the team group is another company called Sparkle. Sparkle is an wholesale global telecom network, which actually has a lot of cables starting from Italy and going towards Asia. And it is actually stopping in Athens, and there are some customers which has data center and data located in Athens. So the main goal was to have basically a backup of all the data in these 2 data centers. And what did we do? We actually implement a QKD link between these 2 data centers, so from TI Sparkle, Coropi, and Metamorphosis. And the link was a 40-kilometer link. Here we had actually only one single fiber, where we co-propagate the quantum channel, which was working in the O band, with a classical channel, which was, working in the C band. You can recognize the QLX, so the QKD, the QKME system, and then here we have actually a first encryptor, which was given by the company called Ribbon. And this encryptor was encryption of layer 1, so physical layer, and it was working at 500 gigabit per second of encryption rate. So here, apart from the use case, it is important to mention 2 things. The quantum channel is co-propagated with the classical channel, so only one fiber is required, no, let's say, more fibers. And the second one is that the key rate of the classical, so of the quantum channel, which was a few kilobits per second, if I remember correctly, 3 kilobits in that case, it was enough to encrypt the data working at 500 gigabits per second. But how is possible this? First of all, we are talking about asynchronous protocols. The first protocol, which is QKD, is up and running, generating keys and storing the keys in the key manager. Then we have another layer, which is, the interface is the key manager, and it is actually working at 500 gigabits. But this encryption is actually done by using advanced encryption system protocol, so like AES protocol. And if to do AES protocol, you need a key of 256 bits. But how often do you need a key? It depends on how secure you want to secure basically your data. So that's the way it works. So most of the communication is actually secured by using advanced encryption systems. This is the reason why you never need the same amount of bit as your same amount of classical information. So basically in most of the communication, you never use the one-time pad protocol. You always use a different type of encryption method. Let's move on to another implementation. Last year there was the G7 meeting summit in Italy, in the city of Bari, and thanks to our basically mother company and so team and Tracy, we have been asked to implement a connection between the location where the prime minister were sitting and the exhibition. The exhibition were the location where all the journalists were sitting and writing papers and sending news around. Here is actually the implementation that we had from this specific use case. Let me start from the bottom. Actually, sorry, let me start from the top and I'll show you. So, Borgo Ignazio, I'm not sure how much you can see, was this beautiful place, beautiful hotel where the prime minister were located. And then there was Bari Fiera, was this big exhibition with all the journalists. We had a trust and node in the city of Monopoly, which is actually super nice. I suggest you to go. But we put just a trust and node. Here is the implementation that we had. In red, we had the quantum channel, Alice, Bob. So trust and node in Monopoly. We had the key manager here, QKME, this one, and this one. So in the trust and node, we only need one key manager because, I mean, we are giving keys to these ones. And then we have different WDM links for the different colors to be used to be sent through the other optical fiber. The use case was to connect a server which was located inside Borgo Ignazio with all the clients located on the other side in the Bari Fiera. And this was a concrete use case that we implemented last year for the G7 summit. I show you also something else, which is one of the most complicated networks that we are implementing. It is actually included in the EuroQCI and in particular in the network of Cyprus, where we installed a very complex network, which was composed by two use cases, use case 1 and use case 2. And here you can only see basically only the quantum network is depicted in the picture. Here you see one rack with a few of the devices that we have been installing, and the nice thing of this network that it was very complex to implement, very challenging, and also it includes an optical switch where the switch was here, and it was used for connecting use case 1 to use case 2. Another important highlight of this network was that we were able to work and to install a quantum software-defined network solution. So from a central node, you can monitor all your link, and you can also exchange the link if some of the links were not working, and this type of solution, and everything was implemented in the past year. Let's move on to another application, to a point-to-point application that I want to show. And it is actually a POC that we did for the police force in Italy. I cannot share, the exact location where we installed the machine, but I can tell you that, what we did was, it was for making a communication between two headquarters of the police, and they had to communicate in a secure way. We install a QKD link, quantum channel in a separate fiber, 30 dB, 100 kilometers. Key manager and an encryption of layer 1, which was realized by an Italian company which is called SM Optics, located in Milan, so in the north of Italy. And this was working at 100 gigabit of encryption rate. So this was used, it's actually used for securing the communication, so the communication between the two different locations. Another implementation that I want to show you is actually a demo that we did at OFC, which is one of the biggest conferences related to optical fiber communication. And here I want to show you, and I like to show this one because we can show that how QKD can be integrated into different type of layers of the ISO OSI stack. What does it mean? Let's start from the bottom again. So here we have a QKD system, Alice and Bob, and key manager exchanging the keys through a fiber. Then the key manager was connected to 3 different applications. The first application was an encryption of layer 1, again from this company, SM Optics, Italian company. The second application was Telsi Musa-X, which is an encryptor of layer 3. And the third application was a video call software called Antares, realized by Telsi, which was at a level 7 application. And it was directly connected to the key manager, okay? So how did it work here? How does it work? The traffic generated by the video camera, so the computer here, was encrypted at layer 7 with the QKD keys. It was sent through this channel to the encryptor of layer 3, encrypted again with another QKD key, sent to another basically channel over here, encrypted again at layer 1, and sent through the fiber and sent through another location. In the other location was decrypted at layer 1, decrypted at layer 3, and decrypted at layer 7. Of course, I mean, this is not, let's say, one specific use case we had in mind, but it was a demonstration on how QKD can be used at a different level of ISO OSI stack, and it is quite important. And but I have also an example that I want to show related to this specific case. So let's assume that you have 2 buildings of the same company, and you want to secure different level of buildings. Let me explain. So on the basement, you might have basically a connection with fibers, and you can install your QKD link. And then you have a very fast, encryption, very fast, basically, machines to send all your classical communication data from one place to another. So here you have your layer 1 encryption on the basement of your building. Then you move on to the third place, and maybe to the third floor. In the third floor, you have switches and floor switches which are installed for different floors, this type of solution in the different buildings. If you take, for example, a cable, so an Ethernet cable, or also, a fiber, you can communicate inside the same building, so we are in a secure location, and you can put a different layer of encryption, so layer 3, for example, or even layer 2 is up to the customer. So basically here we have a communication between different, let's say, floors of the different buildings. Then we move on, and then we have, let's say, very important, the CEO or the CFO of a company wants to communicate with the other people sitting in a different location, and they want to communicate in a super secure way. So what do? They connect their PC directly to the key manager, and they take a QKD key, and then, this traffic can also be encrypted at the third times. So it is, to ensure, to increase the amount of security, but also to make it, more open, to have different type of applications where you can use QKD. Okay, let me now show you a couple of examples when we do another break of different topics, but something that we have been investigating and working on. We do have a project which is sponsored by the Italian Navy, which is called QSUB, where we are developing and working on underwater free space communication link. So the idea is reported in the picture here, where we have an autonomous underwater vehicle, sending quantum signals and classical signal to, let's say, to a submarine, to other type of devices. As I told you, the general idea is not to reach 1,000 kilometers, but it's actually to reach more a few hundred meters. But the concept and the idea has been demonstrated, and we also have some experimental results in this direction. One last thing that I want to mention is that we have been testing our devices, so the QLX, in a free space link. We have been testing both 50 meters and 500 meters, and also next year we are going to test a few kilometers with a time being encoding in a free space link. Here you can see basically the historical building of the Department of Physics in Florence. You can see some of the hills which are around. And this is only a pictorial picture that we took on the buildings. But the idea is, that actually we implemented the link using standard QKD systems, and we are able basically to work and to communicate by using this type of solution, even in a phrase-based link. Okay, so if you are fine, maybe we can have a break now, or do you want to continue? So it's up to you.
I don't know.
Como prefieras. Si
We
quieres.
we had a break in 15 minutes. Maybe yeah.
I have other two topics. Maybe I can do also this one, so quantum fingerprint, quantum digital signature, and then we stop before quantum internet.
Okay.
Okay.
Yeah.
Okay. So, but let's ask if there are questions, what I'm presenting, the use cases, and this type of solutions up to now.
Any question?
No.
No
questions, David.
Okay. So what I have presented basically was the use of QKD keys in some applications, right? And some specific use cases. But there are different type of protocols, and I'm not entering too much into details, but I want to show some ideas which exploit the concept, let's say, of quantum mechanics, but which are a little bit different from a quantum key distribution, in a sense that the long-term goal, actually, of the goal of this protocol, it is actually, to do quantum fingerprint and quantum digital signature. What does it mean? So digital signature, what it is, and how does it work in a classical way? So you have your let's say emitter and your receiver, and what you want to do is that basically you want to sign your document most of the times. How does it work? You have your private password, and then you have your public password, which is being shared. You have your file, and you encrypt your file with a private password, you send it over, and the receiver can open. What's the point? As you can see here, we are still based on asymmetric encryption, basically. So we are facing the same problems that we had in RSA or in the public key asymmetric encryption. So what's the purpose of digital signature? So the first is to ensure authenticity, integrity, and no repudiation of the digital messages. So most of the times it happens, but we are not actually aware that this type of digital signature is happening online when we sign a document, when we save some documentation, and this type of things. So it is happening. So authenticity, what does it mean? It means that we have to verify that the sender's identity. We need to be sure that I was the one sending the message to you. How can you do it? Through a digital signature protocol. What does it mean, integrity? It means that we need to confirm that the message, so the file, has not been altered, has not been hacked. So that's another important property that we want to have and to keep. No repudiation. We need to prevent that the sender from denying that they sent the message. It could be that, sometimes I was not the one sending the message. I was not the sender of this specific message. And we need to being able to identify if it was true or not. You can do it through a no repudiation protocol. How it works, I already explained. Basically, the sender signs with a private key, and the receiver will verify with the sender public key. What is happening in current situation. The problem is that the quantum threat. Classical digital signatures are vulnerable to quantum attacks. So short algorithms can break the underlying public key cryptography. This is the problem, and this is basically something that we have to say. So how do we solve it? We move to the quantum world as well. That's the solution. So what is a quantum digital signature? So it is a cryptographic primitive that exploit and use a principle of quantum mechanics to provide authenticity, integrity, and no repudiation for digital messages. So we need to guarantee the same protocol as reported one slide before, but we need basically to do it by using quantum mechanics. Security basis, it relies on fundamental properties like the no-cloning theorem and the uncertainty principle. Basically, the principles are the one that I presented 1 hour ago with Alice and Bob exchanging photos. It is the same rules and the same parameters which are used. What's the key feature? Again, we are going here to the information theoretic security. So it means that the security is not based to a computational hardness assumption, but it is based on the laws of physics. That's the reason why we want to use a quantum digital signature. Of course, it is, let's say, more complex to implement in the sense that it is different compared to a PQC signature. And let's say the original idea that requires a different technology in the sense that we need a quantum channel, but also we need a quantum memory. It has been, I mean, quite a few examples and new protocols which they don't require a quantum memory, but at least the original idea of the quantum digital signatures, they require a quantum memory. So, but how does it work in practice? So let's say that we have these 3 parties here, and we have Alice, Bob, and Charlie. So the way it works in this way. So we have Alice, which is exchanging basically a key with Bob. And this key basically is called A1. Then Alice basically is exchanging a key with Charlie, which is SP2. And Charlie is actually keeping part of the key, this partial key SP2, sending the keys to Bob. The message, the original message is actually called M, and it is signed by an encryption protocol where S is the encryption composed by M and SK, which is the original message. And Bob is actually doing this type of mathematical implementation. So he's asking if S, which is the message, is equal to basically E, this is the encrypted message composed by M and SK1 XOR XH2. So it's getting both keys from the part 1 and part 2, is able to accept or reject the original message. So it is, let's say, a little bit more complicated compared to the classical one, which is just straightforward, but it will allow you to, to guarantee basically the security of the quantum. So quantum digital signal and the PQC signature. Why? Because as I introduced before, I mean, a PQC is also a valuable solution for generating secure communication and secure digital signature without using the laws of quantum physics. So, very similar to symmetric key exchange, I mean, the PQC signature is based on mathematical algorithms. And you don't need, let's say, I mean, quantum laws of physics, but you can just use, I mean, software-based, and you can run on classical computers. But again, the security is a computational hardness. What does it mean? It is quantum safe. It is secure against a quantum computer. But again, we are sure today, we don't know tomorrow, in a sense that this is what we know today in terms of knowledge about the security of this type of mathematical algorithm, mathematical schemes, I mean, as compared to the quantum computer. Deployment, it is quite easy in a sense that it is quite okay to integrate into existing infrastructure. I mean, you need to change your software, you need to change maybe also a little bit your hardware, it could be, but in general it is feasible. And it has been standardized by NIST in a sense that one of the protocols which has been standardized by NIST, crystal dilithium, and it can be used for digital signature. On the other side, I mean, when you have your quantum digital signature, you have, let's say, something different. Why? Because you are using a quantum mechanical protocol. You require quantum hardware and quantum channels. But I mean, the pro, so the good thing is that you have a security that is based on information theoretic security, which is very important. The deployment requires new infrastructure. We saw it. You need to have, I mean, quantum channels. You need to have quantum hardware. And at the moment, it is a primary research and experimental. So there are no, at least from us, from QTI, we don't have any customer which actually required a quantum digital signature. But I hope that even next year we'll have some. Complementary role, as I was already stressed many times, QKD and PQC are not against each other, but they are complementary, and they complement the overall quantum network. Because we need to remember that we need to create a quantum safe network, independently, from a different type of technology that we are using and we are facing. Okay, so no other questions to what we have seen so far?
No.
Okay, good. So, quantum internet, what it is and why do we need it and why, everybody is so excited about it. In order to define quantum internet, the first thing is that we have to define quantum communication. Quantum communication, I always like to use this definition, which is very simple but effective. And it is the art of transferring a quantum state from one place to another. So if we have a quantum state and want to transfer from one place to another, it is defined as a quantum communication. Quantum communication is actually, it is included, it is needed in a quantum internet because a quantum internet is basically a communication between different quantum nodes. What it is a quantum node? A quantum node could be a quantum processor, a quantum simulation, a QKD application, entangle-based source. So everything which is related to a quantum technology. What do we expect in terms of application from the quantum internet? Here there are 3 examples which are reported here. The first one is secure communications, remote quantum computations, and remote quantum sensing. So the first one is basically QKD and what we have been seeing. Remote quantum computation is that the way that we want to use different quantum simulators to put them together in order to exploit, the multi-device opportunity and to increase basically the sensitivity of our simulations. And remote quantum sensing is a very similar concept, but to do sensing distributed across a network. So, what other application are we looking if we have, a quantum internet? As I said, the quantum computing hub help to protect our data, and then we'll have distributed quantum computers, so we will tackle different problems like financial problems or, how to reduce CO2. If you're going to exploit, quantum simulators, we have new drugs and new vaccines can be investigated and discovered. And if we have a quantum sensor, so we have a greater efficiency in diagnostic tests. So all of these type of new applications will be available, thanks to the quantum internet. But so let's have, a step back and try to understand how it is defined internet. Internet, it is a connection of devices, actually a connection of interconnection of devices. Here we have an example. An example is divided between different networks. We have an enterprise network, phones, computer, routers, switches, whatever. We have a home network, our home network, so PC, tablets, whatever, and we have a mobile network. All of the networks are connected and interconnected by using Internet Service Provider network. This is the way that Internet is working. Similarly, we can define a quantum internet. On the quantum internet, you have different nodes, so QKD nodes, quantum sensors, another QKD node, another quantum computers, and they are connected by using different devices, by using quantum routers, by using quantum repeaters, and by using quantum memories. So all the devices in the network basically are based on quantum principles. What are the similarities and the difference between the quantum internet and the classical internet? Similarities, both networks, the classical and the quantum, are network of networks, so multiple devices are connected together. And the different stacks are divided one to each other. What are the differences? The difference is that in the quantum network, you have a concept like superposition. You have, you're exploiting the no-cloning theorem, you're exploiting entanglement, you have different hardware and different requirements. So there are a lot of differences. But these differences are important in order to exploit and will have a new application, which are completely different from the classical one. So this is the overall idea of the quantum internet and the quantum network. What I want to show in the last 3 to 4 slides, and I want to introduce the concept of multidimensional quantum states, and so basically qubits, and it is a new perspective, and which is something that I've been working for the last 7 to 8 years, up to now. So what is multidimensional quantum state and multidimensional quantum information? In the seminar that I have been presenting and talking, what has happened is that basically we have been using the concept of a quantum bit, so quantum state of light, encoded in polarization or in time. But behind it, there was always the idea that we have a qubit, so the simplest, the corresponding quantum state of a classical bit, where actually we can extract one single bit of information. So in a qubit, we can get basically either a 0 or a 1 at the end of our communication protocol, and then we can measure one bit of classical information. If we increase the dimensionality of our Hilbert space, what means if we increase the dimensionality of the quantum state, from a qubit we move to a qubit, we can encode more than one classical information within the same quantum state. For example, if we have a Q quarter, we can have, so dimension 4, we can encode 2 bits of classical information. If we have a Q8, we can encode 3 classical bits of information, and it goes on in this way. So this is a very important property of multidimensional quantum state. So it means that we have a higher photon information efficiency. Well, it means that when you are measuring basically a quantum state, if you measure a qubit, you get 1 bit of classical information. If you measure a qubit, you can extract more bits of information. The property of this special quantum state is that they have a higher noise resilience. What does it mean? It means that if you put, if you have a plot, if you have a figure where you have your quantum bit error rate, which is one important figure of merit in quantum communication, and on the y-axis here you have the mutual information, so the amount of information exchanged between Alice and Bob minus the amount of information between Alice and Eve. You can see here basically you have a Rocky rate, expected Rocky rate. What you see is that by changing the colors of the figures, of the lines, from black to purple, we are increasing the dimensionality. So dimension 2, dimension 4, dimension 6, dimension 8 is the violet one. You see that the amount of error that can be tolerated actually is increasing. For example, this one, which is the dashed black line, which is the mutual information for coherent attacks, so the most powerful attacks for dimension 2, so qubit, it is 11%, which is actually the amount of information which can be tolerated in a BB84 protocol, which is actually 11%. But if you change from qubit to qubit dimension 8, here actually you move the same protocol from 11% to 24%. So basically you are doubling the amount of Q barrier that you can tolerate your communication. So which is a very, very important advantage in a communication systems. So what we are trying to exploit here at the University of Florence, it is actually a new project that started a couple of years ago, which is called commune, which stands for quantum optical multidimensional network, where we want to demonstrate that it is possible to build new devices based on qubits, not only on qubits. But we have a little bit to reinvent the wheel, in a sense that we need to have a new type of devices. We have to work on the generation of entangled state in qubit. We have to work on the propagation, and we have to work also on the interference. So everything basically is quite new. If you go back basically to go a little bit deeper to the project, the most tricky part is actually the interference, and I try to explain you why. So basically, in a qubit system where you interfere two quantum states, the well-known protocol and effect, which is called Hongo-Mandel, basically, it works like this. When you are sending two photons into big splitters, and if these two photons are identical, they are basically bunching from one side to another. So basically, they are indistinguishable, and they either go one way or the other. And based on this basically effect, you do what the so-called, basically, you can run your entanglement swapping protocol, which is at the basis of a quantum network and of a quantum internet. So it is a fundamental protocol for generating your quantum. The second one is that on the other side, on the qubit system, it is not possible. It doesn't work like this, because there are demonstrations of theoretical groups where they demonstrate that it is not possible to have a similar effect for qubits. So we have been working quite a lot, and we published 2 papers on it. I mean, theoretical paper for now, where we have new strategies and new ideas on how to interfere qubits. So it is possible, and we will demonstrate, we actually demonstrated that there is still advantage, I mean, by using qubits, even if the probability of success is quite low. So this is the research that we done related to interference. Related to the generation, we have been working quite a lot on the generation of high-dimensional quantum states, especially using photonic integrated circuits. And in particular, this is a photonic chip that I have been contributing to when I was at the University of Bristol as a research assistant, so back in 2018. And the idea was to generate entangled source, entanglement state, using a spontaneous Fourier mixing effect, which was allowed by the silicon photonic chips. And we have been able to generate a quantum state up to dimension 15, which was generated in the chip and also measured in the chip. So regarding the generation, we know quite well how to deal with it. The last topic that we have been investigating and working on is the transmission of these quantum states. So you need to think about it is a different states compared to a qubit, and so to transport, you need also a different type of technology. So we, as our group, we have been working on using multi-core fibers. Multi-core fibers are actually fibers which has more than one cores within the same cladding. You can see, let's say, a smaller image here. We have 4 cores, for example, inside the same claddings. We have been demonstrating that these fibers are also kind of special for transporting qubits, because since they are sharing the same cladding, the phase stability between the different cores is quite good. And we have demonstrated that we can keep the phase coherence of the quantum state, for minutes, but actually for hours in these papers. Building on this, basically, we prepared the quantum state. We transmitted through a 52 kilometers multi-core fiber, which is actually installed in the city of L'Aquila, and we measure them. We measure this quantum state, and this quantum state actually demonstrated that it was possible to generate more keys compared to the qubit case, so compared to a 2-dimensional quantum states. So going back to this picture, basically what we have been doing is that investigating a lot on how to interfere qubits. And we have new ideas of a theoretical perspective. We know quite well how to generate qubits using photonic chips. These qubits has been generated inside the chips and can be measured and can also be attached to a communication channel. the communication channel, it has been demonstrated that multi-core fiber are a good channel, a good medium for transporting these special quantum states. And so in the new, let's say, year, we plan to do more experiments towards this direction and exploiting this world. With this, actually, I have concluded all the slides that I had, and I'm here for questions. And I always like to mention these questions, which is quite also, I recognize myself in this question, as actually this statement, and which is that the truth is that everyone is confused by quantum physics. With this, I want to thank you for your attention.
Thank you.
Thank you very much, Davide.
Thank you. I don't know if there are questions.
No, I don't know if anyone wants to ask anything to Davide.
I have you on the last part.
Please.
On the European project. So what degree of freedom are you using for the multidimensional? It's frequency, I guess, no?
No, it's actually path encoding.
Ah, it's path, okay.
Yeah, it's path. So in the chip, basically, we're using different rays, different paths, and then it is connected to the multi-core fiber.
So you have, I don't know, you have, for example, 15 ring resonators or whatever, and you produce a signal idler, and through the chip you redistribute and measure.
Correct.
No? Okay.
Exactly. Yes.
Ah, okay. Yeah. So then you send them through the okay. Because you could add like the layer of the frequency, I guess. If you are using four-way mixing in ring resonators or whatever, you can have you can define signal idler in the in the dips of the rings and all this. But okay, it was in path. And could you tell us a bit more about what is the problem of the interference when you are multidimensional?
So basically, yeah, sure. So in a two-dimensional quantum state, you have 4 bell state measurement, which is the basic principle of making entanglement swapping.
Ah, okay.
When you scale to, for example, to 3-dimensional, you have 9 bell state measurements. Okay. And using linear optical circuit, not non-linear, but just using linear optical circuit, it is not possible to properly recognize, all the different 9 bell state measurements. So it means if you're not, you're making errors, and you're not possible basically to teleport or to swap your entanglement. That's the problem.
Okay. Mm-hmm. Yeah, I think I don't know if this paper comes from your group or you were involved. Because I remember to read a paper where they went a bit. They surpassed the typical efficiency. It's 50%, no, in the Bell state, and they had a bit more of that. I don't remember. It was, I think, a Nature Communications paper. But whatever.
No, it was not. So these ones are the new ones that we put out, only related basically to high-dimensional bell state measurements.
Okay. So because I come from the continuous variable domain, and for us, it's we don't have that problem.
I know exactly.
We have other problems with squeezing, with the amount of squeezing. But we don't have that problem with the Bell state measurements. So.
Actually, here in this paper, we are combining squeezing and discrete variable for making a recognition of these Bell state measurements.
Ah, okay, nice.
Yeah.
I will read it. Okay, so if let me physical review research. 72023. Okay, so if there is no other question, thank you very much for your time. It was like a really amazing overview of cryptography, QKD, quantum internet, and your current research. So we are pretty happy of having you. So thank you very much.
Yeah, thank you very much, David.
Thank you. I will stay connected to hear the other presentations.
Sure.
Okay. So maybe if you can stop sharing and maybe
I already.
Okay. So maybe we can ask Gabriel. I don't know if Gabriel is.
I'm here. Can you hear me?
Yes. So maybe Gabriel, you can share. So
Yes,
Gabriel works at Gradient, and he's going to give us some details about use case that they developed with us using the QKD link we have between Vigo Quantum Communication Center and CESGA. So
Yes,
the stage
thank
is
you.
yours.
Yeah, thank you, David. It's a pleasure to be here in this seminar, this workshop. So yes, I will talk a little bit about a use case we developed in collaboration with CESGA and also University of Vigo on the CESGA-VQCC link. So I'm Gabriel Carral Lopez. I work at Gradient, which is an RTO, technological center, which is specialized in telecommunications. So to give a little bit of context,
Gabriel, we are
Yeah.
seeing the master, not the presentation view.
the master.
Yeah, I mean the how to say, the presenter view.
Yeah, the view, yeah.
Okay. Let me check.
With the next slide.
And your comments.
Yes.
Maybe share window, just window. Okay, now you see it full.
Yeah. Now it's okay.
Okay, it works, no? Changes.
Yes.
Okay, thank you. So yes, we are a telecommunications-based technology center, and okay, we work with CESGA University of Vigo to make a telecommunications use case on top of this fiber infrastructure. So I pertain to the Advanced Communications Department at Gradient, and our expertise is, we work in development of communication systems, and we have a lot of expertise in 5G, 6G deployments, and also autonomous vehicles, and many other stuff, but that's the main thing that we use here for this use case. So, as you know, the problem, you already know what is the problem with quantum computers. When they get finally they will get powerful enough to break asymmetric crypto systems like RSA, Diffie-Hellman, and so on. And these kind of systems are the ones that are used in mobile networks when we connect with our phone to an antenna, and the antenna goes to the internet, and etc. All that infrastructure. Ultimately, its security is based on asymmetric cryptography in that sense. So that's a problem. That's a problem for the future, but we have to start now to think how to solve it. So the key to solve this kind of issue, quantum physics gives us also the answer, no? Which is to use QKD, which David Baco has explained already with a lot of detail, so I will skip this quite fast. So we get back to symmetric shared keys, pre-shared keys. So pre-shared keys has this issue, no? That when if the key is compromised, so cryptographers do not like them so much in that sense that if it is compromised, so the whole communication is compromised. But QKD gives a way, information theoretical safe way to share these keys. So that's the ultimate protection, the holy grail of cryptography, so to speak, for any kind of communication. So what we did, what we thought about is a use case which involves an autonomous vehicle. In particular, it's a unmanned aerial vehicle, UAV, but could be ground vehicle, surface vehicle, whatever. So it's an autonomous vehicle that is connected to an antenna, which in 5G terminology is called the G-node B. And then the G-node B is connected to a 5G core, which is the one that, so to speak, like manages all the connectivity the user, which will be the UAV. It could be a phone, it could be a laptop. In this case, it's the UAV, and so the core manages all the all the connectivity. So the use case, what you could think of is, well, a G-Node B, an antenna, which is in a remote location, and that UAV is connected to the antenna, and then the core is also far away. There is a fiber connection between the G-Node B and the core. So in that we can use that fiber connection precisely used to deploy a QKD infrastructure, 2 QKD nodes, A and B, one in the secure perimeter of the G-Node B, and the other one in the secure perimeter of the 5G core. And keys are distributing between those 2 places in a point-to-point fashion. No? So the thing is that the UAV, can be the control of the UAV, can be some streaming. This is what we did actually, the video streaming that is recorded by the UAV in real time. It can be sensitive information, because you can imagine that you have a UAV and you are like, I don't know, making some recordings of a military base or whatever. You have to monitor to check for intrusions, whatever. You can think of a lot of applications of this. And that information, of course, has to be kept secret and can only be analyzed or seen by the headquarters or the control, the control point which would be situated in this case at the control room at the core location. So, long story short, we have an UAV connected to an antenna, which is sending sensitive information across a mobile network, and we want to secure this using QKD. So what we actually did, because this is a laboratory experiment, it's not a production network, but it demonstrates the principle, no? So we deployed a 5G network. We put the UAV and the G-Node B at Gradient in our laboratories, and we install the 5G core. This is all virtualized in this new paradigm of 5G network, where network functions are virtualized. So the 5G core is we located it at CESGA in a virtual machine, and the G-Node B and the UAV, as I said, were at a 5G lab at Gradient. So we set up VPNs at between these 2 points. The VPNs were based on WireGuard, which is a new protocol, which is different from IPsec, which is maybe the one that you are more used to. And this is a kind of network, a kind of VPN, sorry, that is quite, it's very lightweight in terms of code base, and it's very easy to use. In fact, it's quite trendy, so to speak, and it's replacing other VPN suites based on IPsec for some applications, because yes, that is the ease of use. And WireGuard has a mode which can use a pre-shared key. So it gets a pre-shared key for somewhere else, you can define it, and it mixes it with all the underlying cryptography, and you get PSK plus asymmetric cryptography hybrid to secure your connection, and the security is equal to both of them at the same time. So if one is compromised, the other still works. So what we did was to substitute that QKD key, that PSK, by a QKD key. No? So we end up with a VPN that is protected with QKD in case the symmetric key was compromised. The QKD symmetric key will still protect the connection in any event. So we build starting from WireGuard, we build the software, and we created 2 VPNs. No, so the first VPN connects just the G-Node bit with the 5G core, and that protects. So to say all the signaling information and more network management information, what it's called the control plane, the 5G terminology. And on the other side, we established a VPN between the UAV and the 5G core. which protects the user information and in fact the video signal. So the thing here may be problematic because okay, the UAV is not connected via fiber to the G0D, no? It's an aerial interface, it's RF connection, so it can be protected by QKD. But the use case, has the assumption that the drone, the UAV, can reach the antenna. So imagine that it reaches the antenna for charging, for maintenance, whatever. And when reaching the antenna, it can charge some of the key that has been generated by the QKD infrastructure, no? So in that case, the UAV will make key requests using SC014 interface to the antenna and will receive the keys within that security perimeter. No? And then now we end up with the UAV with keys, also the core and the G0D and the core. So we have the keys in every endpoint of the network. We use the line to secure this some of the connections, and it works in real time with no problem. And we demonstrated that within this kind of infrastructure, you can secure mobile connections with QKD in a very lightweight and easy to deploy way. And this software is open source. Everything was open source wherever it's open source, and the 5G deployment is open source, so it's accessible to everyone, and it's very scalable way of deployment of VPN, QKD VPNs within the mobile networks with the available hardware. And that would be it. So it was pretty fast, but if you have any questions, they are always welcome, of course.
Okay, do we have any question? No. So just to say that both report and the software will be available at CESGA's webpage soon. I hope to do it before the end of the year. So in case you could download it and try. And you have with the report, there is a manual that you can use if you're interested. And of course, you can contact Gabriel if you have any doubt. So now maybe we can pass to Gonzalo here from ITG, that he will, he and Diego Cifrián, they will give us some idea of the use case they carried out with us. So Gonzalo, maybe you can share your screen.
You are muted.
You're muted.
Gonzalo.
I'm sharing, no?
Yes.
Okay.
You're sharing, but okay, no, okay.
Now I'm sharing the
slides.
presentation.
No.
No? Okay.
No, we are seeing
Camera.
your camera.
No. That way. Now, yes, no?
Yes.
Okay. Hi everybody. First of all, I'm going to do a brief introduction about ITG. We are also a national technology center here in Galicia, in Coruña, and also in Vigo. This is our board of trustees, but it's not necessary you know. The technology center is divided in 6 areas from right to left: sustainable construction, digital water, smart energy, autonomous mobility, IoT and industry 4.0, and artificial intelligence and ICT. That is the division or work area that Diego, my colleague, and I belong. In this division, we work with artificial intelligence, computer vision, and LAP mainly. Also in data intelligence with advanced algorithms and machine learning, deep learning, and so on. And also the quantum computing when this demo, this use case was made. Talking about quantum technologies, well, we work in 2 lines, quantum computing. Those are the main things that we are working on. But the group of people where Diego and I work is in quantum communication. In this case, we work with CESGA in this solution that we are going to present now. But also we have a QKD net between these 2 buildings here in Coruña. There are 2 buildings where we work, and we have a QKD net between them that were used or is used in this use case also. And well, finally, this is the most important project that we work in quantum technologies. And this year, well, next year in 2026, starts again with another consortia, but it's a project where we are going to apply quantum technologies in defense scenarios. So, well, this is the briefly introduction about ITG. Talking about our use case, we don't talk with Diego. I think I'm going to do this, and when I need some help, maybe Diego, you can answer. We build a KMS10, TN. It's a key management system with trusted node. The idea is to interconnect different QKD networks and share all the keys between them. In the use case that this is more or less the high-level architecture where we have different nodes that are connecting with a QKD line, as you can see. This one could be the line between Vigo and Santiago that could TI deploy. Maybe this is the ours. It's not 18 kilometers far. It's just 500 meters. And this one could be others. The idea is to share every QKD net keys with the others QKD net in order to every net can send information using these keys instead of being connected. The idea is that the title set is overcoming limitation of the QKD. As you know, QKD has the limitation of the distance. Every time is being bigger, the distance they can cover, but nowadays the technology is quite expensive, and also the limitation of the distance is good to deploy or to build some solution that overcome this kind of limitation. I don't know, Diego, if you want to talk something about the code. This is as the previous use case. Everything is going to be open and published in this year or next or early next year. I don't know, Diego, if you want to say something about that?
Yes, I can explain a bit. It's an object-oriented design that is modular, and we can change things with relative ease. For example, we support 2 encryption modes for the rooted keys. We can either use PQC, in which case we use Kyber right now, but we could use any other algorithm with another class. Or if there is a QKD link available, we can use an hybrid encryption system that uses both Kyber and QKD keys. So we can extend the range while maintaining the same security as QKD has. And we also support two XC protocols, QKD GS 14 and 20. But in the future, we could support other future QKD protocols. And that's it.
This is I can explain that. This is the scenario. As I said, we have 4 different QKD-net. The first one on the bottom is from Ternalia in the Basque Country. I didn't remember the vendor of the QKD system. Ours, that is from Lux Quanta, and also the line between CESGA and Universidad de Vigo, that is the UTI line, and also the Universidad de Vigo, they have their own QKD net. In this graph, just this line and every node have the QKD net. The connection between ITG and CESGA is done by software, and also the connection between Ternalia and our line is done by software. All information that between these different QKD net is sent by using PQC algorithms. In that case, no. In that case, it's sent by QKD. But yes, the thing is, every different node or trusted node connect with others with PQC if they don't have a QKD connection. I don't know if you want to say something more, Theo.
No, that's correct. In the ones where there isn't a QKD pair over the KMSTN, it uses PQC.
Well, now we have, I think, 1 or 3, well, one no, this is one video, but we have some videos. I hope you can watch well. I'm trying to video demonstration. Well, I'm going to stop. Diego, you want to say something that in that case is better from your side? Say stop and
okay. This will share a key between several centers, and you can see the console of the different servers involved. And we will see how the same key arrives to several places.
Just this one is localhost 0, I think, 0, 1, 2, and 3 that are those University of Vigo, ITG, Ternalia, and CESGA places. Well, here you have all the log between the interchange of keys. This is the things we told you in the cases, yeah, ITG-A, ITG-B, Ternalia A and Ternalia B, with the KMSTN, and also the SI, the computer that is asking for the key. Well,
This shows us sending the key request. We are asking for a new key, and we provide the site that is the client ID that is requesting the key, so it is shared with several centers. And now, using the KID, we request it in the other side, and we can see that it replies with the same key.
You have
And we can see it in the console logs.
I think this solution that works well is kind of, you have to believe us that we are sending between all the trusted node. That is done, but now you just can see the information that is in every side.
Here we are requesting the key without a QKD link. So this time it is only PQC encrypted while the key is rooted.
The key is the same for English speakers.
And in the console logs, we can see that the message was encrypted, and the other server in the other side decrypted the message correctly with the key.
Well, here there is another use case. We send encrypted files when they pass QKD.
And the QKD key is being routed through 6 KMSTN nodes.
So because we use this solution to build another use cases in order to not just to sharing the information of the keys between QKDnet, but just to that in the same in that case that we use to control remotely a dog bot, as you can see there. This is another thing that we build between two of the QKDnet. You can send this information encrypted, and here you have logs and the values, and well, Diego can tell you better.
Yes, you can see that it is continuously requesting keys and using it then to encrypt and decrypt outgoing and inbound messages. It works as a proxy, but it is encrypted using QKD keys. It can either use a single QKD key per message, or it can reuse keys. In this case, it is reusing keys, one key for every 10 message, because the QKD is limited in speed, in key rate, and the robot control can be quite demanding. So we reuse keys. It is changing the key every 50 milliseconds or so, even with the key reuse. If we didn't reuse the key, it will use 1,000 of keys. Also, to hide the latency, the key requests are handled in parallel to the message encryption. So it keeps a key buffer. We can see there that is buffered keys. And that way we can avoid the latency of the requesting for new keys, which is really important in real-time control of a bot, because if it responds slow, that is hard to control. And we can see in there that it is retrieving the same key in both ends, and that it is encrypting and decrypting the message correctly.